Hi biologists, the next section we're learning about is the plasma membrane, which remember is the cell membrane that's around every single cell. The key learning attention for this section is the idea that the plasma membrane, remember, it controls the entry and the exit of substances in and out of the cell, and it's selectively permeable, which means it can let some things through but it can't let other things through. So we're always thinking of the plasma membrane as the border of a country, or like the bouncer in a club that's only letting through some things and not letting in others. So what you should be able to do after this section is describe the structure of the plasma membrane in its four main components, and then describe the four main functions that plasma membranes carry out for cells, and know some of the functions that proteins have in a plasma membrane. To get us started, here are some electron micrographs of actual cell membranes. So you can see right down here, a cell membrane is clearly made up of these two lines, and cell membranes are double layered, and we'll learn how that works in this section. So this would be the outside of a cell, and then this is the cytosol with some of the organelles in there. So the structure, like I said, the cell membrane, or the plasma membrane, it's made up of four biological molecules. They're the building blocks of the membrane. The most important one is a phospholipid. We'll learn the details of that next. There's also proteins attached to the membrane that have specific jobs, and there's also cholesterol and carbohydrates that help the membrane to function as well. It is a double layer, and it's the phospholipids that make that double layer. It's like a sandwich, as we're about to see. Phospholipids is just made of a phosphate and a lipid. So remember, what does the plasma membrane actually do? It's found around the outside of every cell, and it's around the larger organelles in eukaryotic cells only. Remember, that's the definition of a eukaryotic cell. If it has membrane-bound organelles, it's eukaryotic. They're the cells that evolved later, and they're much more complex than prokaryotes. And then, like I just mentioned, in the cell membrane, there's proteins and there's cholesterol as well. So here's what it actually looks like when you zoom in. We've got the yellow molecules, which are the double layers of phospholipids. We've got proteins, which are the pink molecules in here, and they're embedded inside it. And we've got carbohydrates attached to some of the proteins, and you can't actually see them here, but there's molecules of cholesterol inside the membrane. So they're the four molecules that build up the membrane. So what actually is a phospholipid? If you know, or you're learning about chemistry, it is made of these molecules. So there's a glycerol molecule attached here. There's two fatty acid chains which are attached at the bottom here. They're like the legs. And there's a phosphate group at the top, which is the yellow circle. And it's the structure of this molecule that means membranes can actually work, and that's how cells have evolved. So the important facts about a phospholipid is the phosphate group is negatively charged. Part of the molecule is ionic, it has a negative charge, and that makes it polar, which means it's hydrophilic. Philic means liking or attracted to. So the top part is attracted to water, it's hydrophilic. Whereas the fatty acid chains down at the bottom, like the legs, they don't have a charge. We call them non-polar in chemistry, and that means they're hydrophobic, and so they repel water. So it's an interesting molecule because the top half is attracted to water and the bottom half repels it. And because of that, if you put a whole lot of phospholipids together in water, they instantly form this layer, or this double layer membrane. So since the tails are hydrophobic, the tails are trying to repel water and they're trying to face away from the water. So you can see the tails face inwards in the double layer sandwich, And the heads are hydrophilic, they're attracted to water, so the heads face outwards. So we've put these molecules into water. Here's water around the top and water around the bottom. And these molecules just automatically arrange themselves to make this layer. And this layer would continue on in each direction, left and right here. So what we call that when the phospholipids make a membrane is the fluid mosaic model. And this is our current understanding of how cell membranes work. They are a mosaic because you've got your phospholipid molecules moving around and it's fluid, so they're constantly moving. But within that, you've got cholesterol molecules and you've got proteins, and they're just embedded inside it. So it's like a mosaic in art, a whole mixture of different components. The proteins can be in different places. So integral proteins, they're the ones that go all the way through. So this large one here and this one here, we call those integral proteins because they're going from the top to the bottom. But then you have peripheral proteins that are actually just attached to the outside. And sorry, this small protein here, that's still called an integral protein because it's inside the lipid bilayer. So if a protein is in the membrane at all, we call it integral. If it's sitting on the outside, it's a peripheral protein. So all these proteins have different jobs. Some of them are to attach the cell to the extracellular matrix, so the liquid that's outside cells and helps them join together. And they also help to attach to the cytoskeleton on the inside of the cell. So you might have tubes of the cytoskeleton attached to the protein, and that helps this particular protein stay anchored where it is. Here's a few other views of the fluid mosaic model. Again, we've got some peripheral proteins attached to the outside. We've got some integral proteins going all the way through. And we've got this channel protein, and we'll learn more about that next week. This is how the cell membrane controls which materials go across the membrane, can enter and exit the cell. So that's the role of proteins. The next chemical that makes up membranes, which I've mentioned, is cholesterol. Cholesterol increases the fluidity of the membrane, which just means how easily it can flow. Like honey has a low fluidity and water has a high fluidity because it can flow. It's less viscous. So cholesterol molecules are just embedded in the membrane. Here they all are. And because they're embedded in the membrane, it's harder for the phospholipid molecules to bond and join together, so it's more likely for them to move around and keep moving. Whereas if you have a cell membrane like this one, where there's no cholesterol, those phospholipid molecules are quite attracted to each other and they'll bond and they'll stick together, and the membrane will slow down and it won't move. And the cells need those molecules to be moving for all the functions to work properly. You can also see up here, as I explained, those phospholipids are constantly moving. When we say lateral movement, they're moving sideways. It's really unusual for them to actually flip-flop and move from the top to the bottom of the layer. If you're in the top, you'll normally stay in the top. Some cells can actually change the fatty acid tails on their phospholipids. You can see here, these tails are all bent and wiggled. So cells can actually control which molecules they put in there. And if you have more kinked and more bent tails, that's also going to make the membrane more fluid. And organisms and cells can actually change that depending on whether it's hot or cold to regulate their membrane. Different proteins in the membrane. There's 6 different functions that they have, and you don't need to memorize them all. We'll learn more about them throughout the year. But I do want to highlight transport proteins in particular. And I mentioned them briefly before. They control which molecules can go into the cell and which ones can go out. So here they are. There's a few different types of channel proteins. This is our focus for next week, so we're actually not going to go into too much detail here. All transport proteins are integral. They're always either a channel going all the way through, or they go halfway through and then they change and open up at the bottom later. All right, the final part of cell membranes are carbohydrates. Again, these are a type of molecule. And as we know, they're an important part of our diet. So we need to eat carbohydrates for lots of energy, and we also need them to add to our cell membranes for them to do these jobs. So carbohydrates help with cell-to-cell recognition. So our body constantly is checking, is this cell part of our body? Is it not? Is this a liver cell? Because cells need to communicate with each other. And they also need to fight off infection. And carbohydrates, those ones sticking out the top of the membrane, they help other molecules to come along and recognize that, this is one of our cells. Or it's a bacteria and it's a foreign cell and we need to attack it with the immune system. And cell membranes also help to join cells together, particularly things like skin cells, where you need them to be joined really tightly to form a waterproof barrier in that organ, in our skin. As I mentioned, there are repercussions in the immune system for our cells recognizing each other. And cell recognition also helps when a baby is first developing as an embryo, and it helps to sort different cells to make our tissues and our organs as they're first growing in our first 9 months. Here are some pictures of what the carbohydrates look like. So they're either attached to a protein here, which is called a glycoprotein. Glyco means sugar or carbohydrate. Or you can have glycolipids, where the carbohydrate is attached to one of the phospholipids in the membrane. And they vary between species. They've got different jobs, but the fact that the chains in these carbohydrates are all different, that's how you can recognize what the cell is and which organism it comes from. And we'll learn more about that in Unit 3, when we learn about the immune system. So, to summarize, the 4 main functions of the plasma membrane. Firstly, it's to be that boundary that's active, it's constantly checking, and it's selective. It's controlling what can go into the cell and what can go out. It's the boundary. The membrane also helps with identity because of those carbohydrate molecules attached. It also helps to receive external signals. That's what some of those integral proteins can do. And because of those transport proteins, it can control which chemicals go in and out of the cell. So that's a signaling protein, and that's some transport proteins, which we'll learn more about next week. And there is a final view of how complex these membranes actually are. So we've got the inside of the cell down the bottom here. We've got the external area of the cell on the outside, the extracellular fluid. We've got our double layer we've got our phospholipid bilayer. We've got our embedded cholesterol molecules. We've got proteins, integral and peripheral. And we've got carbohydrates attached to the end on the outside of the cell.